Module 1, Fundamentals of Petroleum Reservoir Engineering and Fluid Properties. Introduction. Welcome to Module 1 of our lecture series on reservoir engineering. In this module, we will explore the foundational concept of petroleum reservoir engineering, focusing on the physical properties of rocks and fluids, the behavior of fluids in porous media, and how these properties govern the dynamics of reservoirs. This knowledge is essential for understanding the mechanisms that drive the production of hydrocarbons and how engineers manage the complex systems of oil and gas reservoirs. Let us begin by understanding what reservoir engineering is and why it plays a pivotal role in the petroleum industry. Section 1, Introduction to Petroleum Reservoir Engineering. Petroleum reservoir engineering is a branch of petroleum engineering that focuses on the evaluation and efficient extraction of oil and gas from underground reservoirs. It encompasses the study of fluid flow in porous media, reservoir characterization, production optimization, and recovery strategies. The primary objective of reservoir engineering is to maximize economic recovery of hydrocarbons while ensuring the long-term sustainability of the reservoir. This involves analyzing geological, petrophysical, and fluid data to model reservoir behavior under different production scenarios. Reservoir engineers work closely with geologists, drilling engineers, and production engineers to make informed decisions regarding well placement, production rates, enhanced oil recovery methods, and field development planning. Section 2, Physical Properties of Rocks and Fluids. Understanding the physical properties of rocks and reservoir fluids is fundamental to reservoir engineering. These properties determine how fluids are stored and transmitted in the subsurface environment. 2.1 Porosity. Porosity is a measure of the void spaces in a rock and is typically expressed as a percentage of the total rock volume. It determines how much fluid a rock can hold. There are two main types of porosity. Primary porosity, which forms during the initial deposition of sediments. Secondary porosity, which develops after the rock has formed, due to processes such as fracturing or dissolution. Affective porosity refers to the interconnected pore spaces that can transmit fluids, whereas total porosity includes all pores, connected or not. 2.2 Permeability. Permeability is the ability of a rock to transmit fluids through its pore spaces. It is a critical parameter in determining the productivity of a reservoir. There are two key types of permeability. Absolute permeability, which measures the flow of a single fluid through the rock. Affective permeability, which considers the flow of one fluid in the presence of other immiscible fluids. Relative permeability describes the permeability of one fluid phase relative to the presence of other phases. This concept becomes particularly important in multi-phase systems such as oil, gas, and water flowing simultaneously through a reservoir. 2.3 Specific surface of rocks. The specific surface refers to the surface area of rock per unit volume or mass. It influences the interaction between fluids and solid surfaces, especially in fine-grained rocks such as shales. Rocks with a high specific surface area tend to have higher capillarity and adsorption capacity. 2.4 Compressibility of rocks and fluids. Compressibility is the measure of how much a material changes in volume under pressure. Both reservoir rocks and fluids exhibit compressibility. Rock compressibility affects reservoir pressure behavior and storage capacity. Fluid compressibility impacts fluid density and mobility, influencing production forecast and reservoir simulation. Compressibility must be accounted for when performing material balance calculations and pressure transient analysis. 2.5 Fluid saturation. Fluid saturation refers to the fraction of pore space occupied by a particular fluid, typically oil, water, or gas. Saturation values are expressed as percentages and add up to 100% in a given pore system. The three primary types of saturation are water saturation, oil saturation, gas saturation. These values help in evaluating hydrocarbon in place and determining movable versus immobile fluid phases. 2.6 Wettability. Wettability is the tendency of one fluid to spread on or adhere to a solid surface in the presence of other immiscible fluids. It plays a vital role in determining fluid distribution and flow in the reservoir. Reservoir rocks can be water wet, where water adheres to the rock surface. Oil wet, where oil is the preferred phase. Mixed wet, showing a combination of both behaviors. Wettability affects capillary pressure, relative permeability, and ultimately recovery efficiency. 2.7 Surface tension and capillary forces. Surface tension is the cohesive force at the interface of two fluids. In reservoirs, it influences the movement of fluids through small pores. Capillary forces arise due to surface tension and the interaction of fluids with pore walls. These forces can trap fluids in the pore space, leading to residual oil saturation, which affects recovery efficiency. Understanding capillary pressure is essential for interpreting laboratory core analysis and for designing enhanced oil recovery methods. Section 3. Fluid flow through porous media. The movement of fluids through the interconnected pore spaces of rocks is governed by physical laws and rock-fluid interactions. 3.1 Application of Darcy's Law. Darcy's law is a fundamental principle used to describe the flow of fluids through porous media. It states that the flow rate is directly proportional to the pressure gradient and the permeability of the medium, and inversely proportional to the fluid viscosity. While we are not including formulas here, it is essential to understand that Darcy's law forms the foundation for most flow calculations in reservoir engineering. Darcy's law can be extended to account for multiphase flow, nonlinear flow regimes, and anisotropic conditions, which are common in real reservoirs. Section 4. Reservoir drives and races. The drive mechanism in a reservoir determines how hydrocarbons are displaced from the reservoir to the production wells. Understanding drive mechanisms is critical for predicting production performance and selecting recovery strategies. The main reservoir drive mechanisms include solution gas drive. Energy is provided by gas coming out of solution as pressure drops. Gas cap drive. A gas cap expands and pushes the oil toward production wells. Water drive. Water from an underlying aquifer pushes hydrocarbons toward the wellbore. Gravity drainage. Gravity causes the heavier oil to move downward while lighter gas rises. Combination drive. A combination of two or more mechanisms. Each drive type has implications on recovery efficiency, production rates, and reservoir management strategies. Section 5. Hydrocarbon content and reservoir composition. Hydrocarbon reservoirs consist primarily of oil, gas, and associated fluids trapped in porous rock formations. The composition of these hydrocarbons affects their physical behavior and how they can be produced. 5.1 Hydrocarbon composition. Crude oil is a complex mixture of hydrocarbons ranging from light gases to heavy components. Natural gas is mainly composed of methane, with varying amounts of ethane, propane, and other light hydrocarbons. The composition influences properties such as density, viscosity, volatility, phase behavior. Understanding the composition helps in classifying the reservoir fluid and determining the appropriate production and processing methods. 5.2 Reservoir fluid classification. Reservoir fluids are generally classified into dry gas, wet gas, condensate, volatile oil, black oil. Each class has distinct pressure, temperature, behavior, and recovery characteristics. Section 6. Water and its physical properties. Water is a significant component in most petroleum reservoirs. It can exist as connate water, edge water, or bottom water. Key physical properties of water in the reservoir context include density, viscosity, compressibility, solubility with hydrocarbons, formation volume factor. Water can play a beneficial role in providing drive energy or pose challenges such as water coning and production problems. A proper understanding of water behavior is necessary for efficient reservoir management. Section 7. Gas behavior and phase behavior of hydrocarbons. The behavior of gases in reservoirs follows the laws of thermodynamics and is influenced by temperature, pressure, and composition. 7.1 Gas behavior. At reservoir conditions, gases do not always behave ideally. Real gas behavior is considered through correction factors. Gas compressibility, Z factor, and formation volume factor are all essential for evaluating gas reserves and designing production systems. 7.2 Phase behavior of hydrocarbon systems. Phase behavior refers to the manner in which hydrocarbons change phase, gas, liquid, or solid, under varying pressure and temperature conditions. There are three types of systems commonly studied. Single-component systems, containing only one hydrocarbon. Binary systems, containing two components. Multi-component systems, containing a complex mixture of hydrocarbons. Understanding phase envelopes, critical points, and phase transitions is essential for designing surface separation facilities and predicting reservoir performance. Summary of Module 1. In this module, we have covered the foundational aspects of reservoir engineering. We introduced the concept of petroleum reservoir engineering and delved into the key physical properties of reservoir rocks and fluids. We also explored fluid flow through porous media, the types of reservoir drive mechanisms, hydrocarbon compositions, and the fundamentals of gas and water behavior. In Module 2, we will dive deeper into PVT analysis, equilibrium concepts, sampling techniques, and methods for evaluating and interpreting reservoir fluid properties.